Welcome back to SciInsights. Don't forget to subscribe.
Today, about 98% of the atomic matter in the universe consists of hydrogen and helium. But thanks to threshold 3, that other 2% is made up of all the other elements in the periodic table. That makes some amazing things possible because these different elements can combine to form an almost infinite number of different types of matter. Objects that are much more complex than stars could now form. Objects like planets. And that was the work of threshold 4. Here's how it works. When new stars are formed, they're surrounded by huge clouds of chemically rich matter, are ingredients for this threshold. These clouds spin in different orbits around the newly forming star, creating Goldilocks conditions that are just right for elements to combine. Some atoms combine chemically to form a variety of different molecules, but also atoms and molecules often clump together to form bigger and bigger lumps of matter. This process is called accretion, and eventually it goes on to form entire planets. Now, since lighter elements are much more plentiful in the universe, many planets consist mainly of hydrogen and helium, like Jupiter and Saturn. But because hydrogen and helium atoms are so light, intense radiation sometimes blasts them away from regions close to the new star. Those regions then contain a relatively high concentration of other heavier elements. And eventually these elements may clump together through accretion to form solid planets, such as our Earth. In our planet's crust, for example, the most common elements are oxygen, silicon, aluminium, and iron, not hydrogen and helium. Our Earth formed about 4.5 billion years ago, but the very first rocky planets may have formed within 1 billion years or so of the Big Bang. These planets represent new forms of complexity because they contain a much greater diversity of chemical substances than had ever existed before, and that could create even more complex entities, such as the first living organisms.
Imagine you're in a time machine and you've travelled back 4.5 billion years. And what you're doing is you're taking a stroll on the early Earth. Now, what would it be like? And would you be having fun? Well, the answer is, I don't think you'd be having much fun. First, you'd be walking on molten lava. Not nice. Secondly, you couldn't breathe because there's no oxygen. You'd be asphyxiating. And thirdly, you'd be ducking asteroids and meteorites that are crashing into the early Earth, lots and lots of them. And fourth, you'd probably be throwing up because of very high levels of radiation. And if you stayed there too long, your hair would start falling out too. So I don't think you want to stay there too long. Why was the early Earth so hot? Because that's the main thing, it was really, really hot. Now you've already got some clues as to why it was so hot. And you might be able to think this through. But let me give you 3 of the main reasons. First, do you remember that supernova that blew up just before the solar system was formed? That created huge amounts of radioactive material. And that radioactivity generated a lot of heat. Today, a lot of it's dissipated. So today's Earth is nothing like as radioactive as it was 4.5 billion years ago. Secondly, you remember the process of accretion, really violent, lots of space debris crashing into other space debris. Each collision with a meteorite or an asteroid created huge amounts of heat. And the third problem is subtler because it's pressure. You remember those clouds that the early stars formed from? Well, as the clouds got denser, you remember, the pressure increased and they got hotter. And the same thing happens with the early Earth. As it accreted, it got larger, pressure built up and heat built up, particularly at the center. So that's why the early Earth was so hot. In fact, the early Earth got so hot, it melted. And that is really important, because if it hadn't melted, today's Earth would be very different from the way it was. To get a sense of what happened and why this was so important, let's imagine a kind of absurd experiment. Okay, so you're going to put some stuff in a saucepan. You're going to put in some coins. You're going to put in some rice. You're going to put in some plastic. Let's add a bit of mud. Let's put in some ice. And then you can chuck in one or two other things. And now we're going to heat that stuff up to several thousand degrees. Don't stir. Just let it simmer. Now, it's not going to taste good, but we may be able to learn something from this. And what we'll see is that the whole thing's going to melt. The heavy stuff, such as the coins, are going to sink down to the bottom. Lighter stuff is going to rise to the top, and some stuff is going to evaporate and boil above the saucepan. Now, something very like this seems to have happened to the early Earth. It melted, and because it melted, it formed a series of layers, and they give it its structure today. Let's look at the four main layers. Now, the first is at the center. It's the core. It's metallic. Nickel and iron, above all iron, sank to the center of the Earth. And the fact that the center of the Earth is full of metal is really important, because this gave the Earth its magnetic field, and the magnetic field deflects some of the sun's rays that would be harmful to living creatures such as us. So that's the first layer, the core. Secondly, lighter stuff, lighter rocks float above the core and form a layer that's called the mantle. Now, the mantle you can think of as a sort of hot sludge of rocks. These rocks are so hot they're sort of semi-molten, and they're actually moving around in convection currents inside the mantle. And then at the very top you have a layer called the crust. Very light rocks such as basalts and granites reach the top, they cool, they form this thin layer, the crust. That's where we live. But the crust is pushed around by those convection currents from underneath. You can think of the crust as a tiny thin layer, a bit like a sort of eggshell. And finally, the fourth layer, the atmosphere. Some of the gassy stuff bubbles up to the top, it evaporates. The very light gases, such as hydrogen, disperse into space. But a lot of other gases just hang around the Earth, held by its gravitational pull. And that's how the Earth acquired the structure it has today. All of this happened about 10 million years after the creation of our solar system. Now I want you to hop back in that time machine. And what I want you to do is to take off from your backyard and hover over your hometown. And now I want you to put the time machine into fast motion, so it's moving rapidly back through time. And you're going to see something really weird. What you're going to see is that the land is going to start buckling and shaking and moving like a huge monster. This looks weird to us simply because we don't live long enough to see that the Earth is in fact changing all the time. Now, in fact, some scholars began to notice this as early as the 16th century when they studied the first world maps that were ever produced. Some of them noticed odd things, like the fact that West Africa seems to fit well into Brazil. I mean, look at a modern map and you'll see the same thing. In the early 20th century, a German meteorologist called Alfred Wegener found lots of evidence to suggest that the continents had in fact once been connected. For example, he found very similar geological strata in West Africa and in Brazil. And during World War I, he wrote a book arguing that once all the continents on Earth had been united in a single supercontinent that he called Pangaea, after the Greek goddess Gaia for the Earth. Now, what did the other geologists think of this great idea? They were not impressed. Here's the problem. Wegener came up with heaps of evidence to show that the continents seemed once to have been linked. What he couldn't do was explain how the continents moved around the Earth. So when they said, okay, Alfred, how do you tow a whole continent around the Earth? He couldn't explain it. And as a result of that, his great idea was ignored for almost 40 years. We saw when looking at astronomy that quite often new technologies can generate new evidence which changes our understanding of the science. And something very like this happened in geology. During World War II, sonar technologies were developed to track submarines. And after World War II, some geologists used that technology to try to map the ocean floor. And when they started doing this, they found something that really surprised them. Through many of the Earth's oceans, they found huge chains of volcanoes. And what's happening is that lava is coming up from the mantle, it's rising up, it's forming mountains, and it's pushing apart the old oceanic crust. In the center of the Atlantic Ocean, for example, there's a huge chain of these mountains, and what they're doing is they're pushing the Atlantic apart. So the Atlantic is actually getting wider and wider at about the speed that your fingernails grow. Now, some geologists thought, okay, does this mean that the Earth as a whole is just getting bigger and bigger and bigger like an inflating balloon? But they soon realized that elsewhere in the Earth, crust was going back into the mantle, which balanced what was happening in the Atlantic. Let me explain how it works. Now, to understand this, you need to think of two basic types of crust. There's continental crust, which is the land that we walk on, and then there's oceanic crust, the land beneath the oceans. In general, continental crust is lighter. It tends to be made of granites. Oceanic crust tends to be heavier, made of basalts. Okay? Now, once you've got that, think of two bits of crust colliding, continental and oceanic. What's going to happen? Well, what's going to happen is that the heavier oceanic crust is going to dive beneath the continental crust. Now think of this. It's grinding against the continental crust. It's creating huge friction and lots of heat, and it melts part of the continental crust and punches up whole mountain chains. And that basically is how the Andes mountain chain was formed. Mountains can also form when portions of continental crust collide with each other, but this time, because both portions have about the same density, they don't dive beneath each other, but they crumple up to form huge mountain chains. And that's basically how the Himalayas were formed about 50 million years ago, when India crashed into the mainland of Asia. Now, there's another type of relationship between different parts of crust. Sometimes you get two bits of crust that are moving in opposite directions past each other. What happens is that the friction holds them, but the pressure builds up and then suddenly they slip. This is what's happening along the San Andreas Fault in California, and it's that slippage that creates earthquakes. Okay, these are the basic ideas of the modern theory of plate tectonics. And the theory of plate tectonics is the fundamental idea of modern geology and earth sciences, just as Big Bang cosmology is the fundamental idea of modern astronomy. It explains a huge amount about how the Earth works, just as Big Bang cosmology explains how the universe works. It explains, for example, why all around the Pacific you get a ring of volcanoes and earthquakes. It explains why the Earth is broken up into a series of plates, like a broken eggshell, and why it's around the edge of those plates that you get violent activity such as volcanoes and earthquakes. It explains how mountains form. It explains all the fundamental features of our Earth, and also how the continents move. It explains what Wegener couldn't explain. So the theory of plate tectonics is now the most fundamental idea in modern earth sciences.
Thanks for watching.